Okay, key for your test review. Number 1, y equals 5 to the negative x power minus 2 has a graph that matches the parent graph, shifted 2 units. Okay, so this minus 2 right here, that is a vertical shift, so it's 2 units down and reflected over the blank axis. So if my x is negative, that is reflected over the y-axis. All right, number 2, y equals 1/2 log base 3 of x minus 1 has a graph that is increasing or decreasing, circle 1, has an x-intercept of blank, and has blank as an asymptote. So I think on this one, it would help if we had an idea of what was happening with the parent function here. So this is a log function, and the base is 3, so it's greater than 1, so it's going to look something like this. So that is definitely increasing, but I got to make sure there's not a reflection here anywhere. And the only one that would, what would matter if I was reflecting over x or y, but I'm not reflecting it on either one of them, so even if I shift this around, it's still going to be increasing. The x-intercept, all right, so let's look at what's actually happening here. So this is my original one, and then this is where my key point starts. That 1/2 makes this a vertical compression, and so that doesn't change my intercept or anything here. And then that x minus 1 means I'm going to move it to the right 1. All right, so it's a horizontal shift right 1, which means that the asymptote also shifts, and so that's going to look like this. It's supposed to look more compressed than that. I don't know that I did a great job of that, but the x-intercept is an ordered pair. That is now at 2, 0, where the parent function is at 1, 0. And the asymptote is the equation x equals 1. All right. So next we're going to sketch each of the following, showing at least one specific point, and the asymptote. The asymptote needs to be on there as well. I would suggest that you have in your mind, or really even better, to have a little sketch of the parent function. It's kind of the whole idea of this. And this is an exponential, which means that for my parent function, I'm going through 1, and the base is a fraction, so for the parent function, it looks something like this. Okay. So I'm going to take this key point here, okay, and that's where my actual beginning key point is there. This negative right here means that it's going to be a reflection in the x-axis, so it would reflect down to here. That's now where the point is. Then after it's reflected, there's a vertical shift of 3 up. So from here, I'm going to go 1, 2, and 3, like this, and that's where it actually lands. Right? So started here, reflected to here, and then shifted up 3. Now when I reflected it, the parent function looked like this, right? It reflected, my asymptote was at y equals 0, so it stayed there when I reflected it. But then when I shifted it up 3, okay, when I was here after the reflection, the asymptote is here at y equals 0. So the asymptote gets shifted up to 3. So there's my asymptote. And then the curve looks like this. But better, always but better. And then you want to make sure that it is obvious where these points are, right? This is 1, this is at 2, this is at 3. Okay? Label where things are. You need your asymptote and a key point on there. If you have 3 hash marks, I'd be okay with that, saying that this is 2 and this is 3, but you can't just randomly put one somewhere. Okay, so for number 4, this is an exponential. So an exponential with the base that's greater than 1, parent function looks like this. So my key point starts here. Then that is negative x, which means that's a reflection on the y-axis, which doesn't change where this point is. And then it is shifted down 1, so now it's here. My asymptote was at y equals 0. When I reflect on the y-axis, that doesn't affect it. I have to go answer the phone. Okay, so it's been about 25 minutes since I stopped on here. I have no idea what the last thing is that I said. But I know that we figured out that our original point was here, and then we shifted down 1. Right? And then we had a reflection in the y-axis, which means instead of this shape, it's coming the other direction, and our asymptote was at y equals 0, so now it is at y equals -1 because it was a vertical shift. So my curve looks something like this. There you go. All right, so then for number 5, have a log. The base is, which means I'm going to go through 1, 0. The base is greater than 1, so it's going to look something like this. All right, so here's my key point starts here. This negative means that this is a reflection in the y-axis. So, I'm sorry, it means that this is a reflection in the x-axis, so that means that this doesn't move. This point doesn't move. And then this is 1/2 times x, which means that we do the inverse of this, which means I'm going to multiply it by 2. So since this is at 0, 1, this now becomes here at 2. Right? It's not a shift, it's a stretch. So since I have a horizontal stretch, my asymptote stays the same. It just got stretched. And then the reflection was in the x-axis, so instead of the shape looking like this, it's going to come down like this. And that's what I would have there. Okay. Now, domain and range for each exponential or log. For all of these, in your mind or sketched on your paper, you need to be thinking of the parent function first. So I have the parent function here. This is an exponential, so here's my point right here. This is what the parent function would look like. So when I take this exponential and I shift it down 2, okay, it's a vertical shift of 2, my point goes from there to here. It also means that my asymptote shifts down 2, and it's going to look like this. Okay, now, it doesn't ask you for the graph. You don't have to graph it. That's what's going to help you with the domain and range. The domain is all real numbers. The range goes from -2 to infinity. Here I have a log function. B is greater than 1, so it's going to look like this. Okay, so I have here, and then this is a vertical shift of 3. So 1, 2, 3 comes to here. My asymptote was at x equals 0, and it still is. My shape looks the same. It just all got shifted up, so something like this. So my domain, starting at 0, going to infinity, don't include either one of them, and my range is all real numbers. Number 8. My y-intercept and asymptote for this. So again, I'm going to start with, actually, I'm going to do this differently. I'm going to do it. There's not much room right here. So I'm going to do number 8 right here. My parent function, it's an exponential, so it's going to look like this. Right. And I'm looking for my intercept and my asymptote. So here I know my asymptote is at y equals 0. So that's the parent function. Then all of this happens here. Okay, so I have the exponential. My key point starts here. That is a vertical stretch of 5. So my y values get multiplied by 5. So I'm here at 1. 1 times 5 is 5. 2, 3, 4, 5. So now I'm here. So I've stretched it, which means I haven't moved my asymptote yet. My asymptote is still at y equals 0, and I have stretched it from 1 to 5. And then it's a vertical shift of 4. So then I go up 1, 2, 3, 4 more. But the only thing here that affects my asymptote is the stretch. I'm sorry, not the stretch. It's the shift. So if I start off at y equals 0, then I go up 1, 2, 3, 4. Here's where my asymptote is. Remember, there was a stretch of 5, so it looks something like this. Oh, or better. Always better. Oh, close enough. So that tells me then my intercept, my y-intercept, is at 0, 9, because I went up, I was at 1, went to 5, and then went 4 more. So this is at 0, 9. And my asymptote, which is was at y equals 0, is now at y equals 4. Okay, so then for number 9, do my little graphs right here. And this is a log. So it looks like this. That's my parent function, right? Got at 1, and then my asymptote here would have been at x equals 0. So this negative right here means that this is a reflection in the x-axis. So if I'm starting here and then it's a reflection in the x-axis, nothing, it gets shifted, okay, which just means it's going to look like this now. And then this x minus 3 means that it is a horizontal shift to the right 3, so I end up here. When I shift, my asymptote shifts as well, so there's my asymptote. And my curve, instead of looking this way, goes, oops, goes this way. All right, so my intercept, my x-intercept is going to be at 4, 0, and my asymptote is at x equals 3. Okay. All right, next page. Again, none of those, except the ones that said you have to sketch, do you have to sketch. But that is going to be the best way for you to figure out what the heck is going on. All right, number 10. Okay, so I did 11 in class. I'll just talk you through it again since it's in here and I didn't erase it, and I will do number 10. All right, so my suggestion, the way I think that the best way is to do this, that's always a matter of opinion, is to think about the parent function, right? This is an exponential, so my exponential looks something like this. So this right here represents f of x equals 2 to the x. And then I'm going to pick points that would be good for my parent function. So my parent function points are -2, -1, 0, 1, and 2. So when I substitute these into the parent function, 2 to the -2 power is 1/4. 2 to the -1 power is 1/2. Then this is 1, then this is 2, then this is 4. Okay, so my x values, the sign changes on x, right? This is -x. So I just change the sign. So this becomes 2, this is 1, 0 is still 0, -1, and -2. Then for my y, two things are happening. I'm doubling the y, and I'm subtracting 3. So 2 times 1/4 is 1/2, and then 1/2 minus 3 is -2.5. 1/2 times 2 is 1, and 1 minus 3 is -2. 1 times 2 is 2, minus 3 is a -1. 2 times 2 is 4, minus 3 is 1, and then 2 times 4 is 8, minus 3 is 5. So my pink points are my new points. Those are the ones that I'm actually graphing. My green ones were from my parent function. And I just looked at the transformations there. So now I'm just going to go and graph these points. And again, from here, you should have an idea of what's going to happen, right? This -x means that it's a reflection in the y-axis, so the shape is going to now look like this. There's a vertical stretch, and it's shifted down 3. Okay, so you kind of have something that will probably look like that. All right, so I'm going to graph 2, and then -2.5. I'm going to graph 1 and -2, 0, -1, -1, 1, -2, 5. Which means that since I had a shift down of 3, that my asymptote is here at -3. That always needs to be graphed as well. And then my graph looks like this. Oh. What's bigger? Okay. And there you go. So it's been stretched, reflected, stretched, and shifted down. Then on this one, just talk you through it again, I would look for my parent function. Here's my parent function, If I rewrite it as an exponential, I get this. So I'm just going to, but here, when I do these, I'm going to pick my points for y. So I'm picking -2, -1, 0, 1, and 2. And when I substitute those in for y, these are the x's I get. So my purple points here are from my parent function. Here's my parent function. Here's the parent function written as an exponential. Then I look at my transformations. All right, well, my y's get multiplied by a -1, so the sign changes on the y. And the x, this is 1/2 times x, so anything inside the parentheses that's happening with x, we do the inverse. So instead of multiplying it by 1/2, I'm dividing it by 1/2, which is the same as multiplying it by 2. That's where these numbers come from. And then here is my graph. All right, so I'm going to solve each exponential equation here. Number 12, I've got 8 to the 2x plus 2 power, and then that equals 64. So although I could get these down to a base of 2, I don't need to because then I can make that 8. So 8 to the 2x plus 2 power equals 8 squared. So 2x plus 2 equals 2. So 2x equals 0, and that means x equals 0. So here I've got 6 to the x plus 2 power. And that equals, well, 1 over 36 is the same as 1 over 6 squared. So that can be 6 to the -2 power times x. That means that x plus 2 equals -2x. So 2 equals -3x, and x equals -2/3. Then we did this one in class. I can talk you through it again. The 16 to the x power equals 128 times 32 to the 1/4. So I got to figure out what my base should be. 4, I can't really get 4 to an exponent to give me 32, so I got to break it down to the 2. So 2 to the 4th power is 16, so this becomes 2 to the 4x. 2 to the 7th gives me 128. 2 to the 5th gives me 32, and this is the 1/4 power, so that's where I get my 5/4 from. So the left-hand side, I just rewrote it. When you multiply two terms with the same base, you add the exponents. I know you know that. Make sure you don't do some weird thing there. So now we have the bases the same as 2, so 4x equals 33 over 4. Solve for x, we get 33 over 16. Okay, number 15. I have to isolate the base, which means I do not get to multiply the 9 times the 16. That makes no sense. I'm going to divide both sides by 9. So this gives me 16 to the -x equals 8. So the base that I'm going to need is 2. So 2 to the 4th gives me 16. So this would be to the -4x. And that equals 2 to the 3rd. So -4x equals 3. So x equals -3/4. All right. Next page. So we're going to evaluate each logarithmic expression. So log base 4 of 1/8. That means I'm going to make these equal to k. So 4 to the k power equals 1/8. So my base is going to have to be 2. So this is 2 to the 2k power equals 2. I know it's going to have to be negative because I got to get it out of the denominator. And then 2 to the 3rd is 8, so it's 2 to the -3rd power. That means then that 2k equals -3, which means k equals -3/2. So this equals -3/2. So then here, there's no base here. The base is 10. So 10 to the k power equals, I'm going to change this to a fraction. So this is tenths, hundredths, thousandths, 10,000ths. This is 1 over 10,000. That's 1/10,000th. That means that 10 to the k equals, well, 10. This is going to have to be negative because it's in the denominator. And then to get to 10,000, 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, so that's a -4. So k equals -4. this equals negative 4. All right, so I did this one in class. Again, I'll just talk you through it. There's 2 different ways to look at this. But the natural log of 1 over the 5th root of e to the 4th gives me the natural log of 1 over e to the 4/5 power when I write this as a rational exponent. And then to get it out of the exponent, or I'm sorry, get it out of the denominator, that becomes a negative exponent. So the natural log of e to anything just gives you the exponent. So bam, that's just your answer right there. But you can also set this equal to k. So the base is e to the k power equals this fraction right here. And again, it becomes negative to get it out of the denominator, and then that gives you your answer right there. This basically is why you can just jump to the negative 4/5 here. Either way. That works. All right, so 19. I'm going to get 1/4 to the k power equals 16 to the 3rd. So I can leave 1/4 as my base. So 1/4 to the k power equals 1/4. All right, so that means it's going to have to be negative because I put that in the denominator, and that's going to be squared, so it's going to be 2 times 3, which is negative 6, and then I'm really just done. That means that k equals negative 6, so this equals negative 6. Okay, number 20. Log base 8 of 3 minus log base 8 of 24, so I need to condense these. So since this is minus, it's going to be division. So log base 8 of 3 over 24. That's going to give me log base 8 of 1 over 8. Now I could write it as an exponential. So this is going to give me 8 to the k power equals 1/8, which means that 8 to the k power equals 8 to the negative 1 power. So k equals negative 1. This equals negative 1. All right. Now I have these 2 again that I need to condense. So this is going to give me log base 1/3 of 9 times 9, which is 81. Then I can set that equal to k. So 1/3 to the k power equals 81. So my base is going to be 1/3. It means I get 1/3 to the k power equals 1/3. Right, so this is going to have to be negative. I know that. All right, and then 3 to the 4th power is 81. So this is a negative 4. So k equals negative 4. So this equals negative 4. 22. This 1/2 right here becomes the exponent, so this becomes log base 11 of 121 to the 1/2 power. That's the square root of 121, so log base 11 of 11. So the log of when the base and the argument here are the same, that means it's just 1. If you're not real sure, you can take 11 to the k power, and that equals 11 to the 1st power, so k equals 1. But when these 2 match, the answer is just 1. So this is 1. Log base 2 of 64 times the square root of 8. This is going to give me 2 to the k power is equal to 64 times 8 to the 1/2 power. So I need my base to be 2. So 2 to the k power equals, well, to get 64, 64 is 2 to the 6th power times 2. All right, 2 to the 3rd is 8. And I have this 1/2, so that makes this 3/2. These 2 exponents here need to be added. So this is going to become 2 to the k power equals, so I need a common denominator. That's going to be 12 over 2, so it's going to be 2 to the 15 halves power. And that means that k equals 15 over 2. There you go. Okay, 24. I'm going to solve these equations, and I have the log with matching bases on either side, which means that these two pieces are just the same. So 35 is equal to x squared minus 2x. It's a quadratic, so I set it equal to 0. So x squared minus 2x minus 35. So 0 is equal to, these are both x. It's going to be 5 and 7. That's a negative 7 and a positive 5. So my solution set here is positive 7 and negative 5. Then I have to check for extraneous answers. When I substitute in 7, everything works fine. This negative is my concern. But negative 5 squared is a positive 25. And then minus 2 times a negative 5, that would give me a positive 10. So this ends up being positive, which is really all that really matters. And so these both work. Those are both my answers. 25. So log base 1/5 of 125 equals x plus 1. So I don't have the log on each side. I'm going to use my exponential rules here. So 1/5 to the x plus 1 power equals 125. So I'm solving this just like I did on the ones above. It's going to give me 1/5 to the x plus 1 equals 1/5. Okay, so it's going to be negative because now my number's in the denominator. And 5 to the third power is 125, so this is negative 3, which means I get x plus 1 equals negative 3, so x equals negative 4. Okay, 26. I'm going to handle this the same way as an exponential, so x to the 4/3 power equals 81 over 16. I'm going to need to get x by itself, so if I take it to the power of the reciprocal of 4/3. I take both sides to the 3/4 power. That'll make this just x. This becomes 81 over 16 to the 3/4 power, which means that I get 81 over 16 cubed, and then I'm taking the 4th root of that. I could cube it and then take the 4th root, or I could try and take the 4th root. So can I figure out the 4th root of these two? Well, what to the 4th power gives me 16? That would be 2. What to the 4th power gives me 81? That would be 3. So if I go ahead and take the 4th root, this is going to give me 3 over 2 cubed, which is equal to 27 over 8. So x equals 27 over 8. All right, on 27, I need to condense these here. So this 1/2 is going to have to come up and be the exponent here. The 4 comes up and is the exponent, and the 3 comes up and is the exponent. So this is going to give me log base 5 of 5 to the 4th power minus log base 5 of 25 to the 1/2 power, and that equals log base 5 of x to the 3rd power. So now I'm going to work this out a little bit. 5 to the k power, let me write this out so I don't lose you, but I can simplify this without actually taking that to the 4th power. Just taking this part, if I figure out what this is from the exponents, 5 to the k power would be equal to 5 to the 4th power. So k is just 4. But remember, if you have a log with the base, these two bases match, then this is just what you have left. So this just gives me 4 minus, then log base 5 of, well, 25 to the 1/2 power is the square root of 25, which is 5. So I just have log base 5 of 5, which is 1. And that's equal to log base 5 of x cubed, which means that 3 equals log base 5 of x cubed. So when I change this to an exponential, 5 to the 3rd power equals x to the 3rd power, which means x equals 5. Alrighty. here. I need to condense these first. So log base 6 of x times x plus 5 equals 2. So log base, well, I can go ahead and, I'll lose you. So log base 6 of x squared plus 5x equals 2. So change this to an exponential. 6 to the second power equals x squared plus 5x. So 36 equals x squared plus 5x. Which means then that 0 is equal to x squared plus 5x minus 36. So 0 equals, this is going to be x plus 9, x minus 4. I don't know if you can see I don't know if you can tell that the thing is shaking. Oh, somebody's banging upstairs and it's making my board shake. So I don't know if it's shaky for you, but so x plus 9 equals, or I'm sorry, x plus 9 times x minus 4, which means that my solution set is a -9 and a +4, but then I have to check for extraneous answers. And remember, you always go back to the original one, because that's the domain that matters. When I substitute in the -9, this will give me a log of a negative, which is a big no-no, so that is an extraneous answer, and my answer is just 4. Number 29. The 3 becomes the exponent here. It's the only one I have to worry about. So this is going to give me log base 5 of x cubed times 4, because when I condense these, so this is really 4x cubed, equals log base 5 of 500. So then the logs match. I got log base 5 on both sides. So that means that I get 4x cubed equals 500. So x cubed equals 125. Cube root of 125 is 5. So x equals 5. Alrighty. Number 30. Okay, there's not a whole lot of room for these. So I think I'm going to, let's see, I'll rewrite that on the next, I'm going to rewrite 30 and 31 on the next page, because I can't cram it all in there and make sure that you can read what I'm even writing. So log base 3 of 81 a to the 4th cube root of b all over 27 c to the 7th, like so. Okay, so I'm going to take this and I'm going to expand and simplify. So the first thing I'm going to do is just expand it all. So in the numerator, all of these are being multiplied, so that all becomes addition. So this is going to give me log base 3 of 81 plus log base 3 of a to the 4th plus log base 3 of b to the 1/3. And then these are in the denominator, so this is minus log base 3 of 27 minus log base 3 of c to the 7th. All right, so I've got some little side work that I need to do here. I can actually simplify this. So this is going to become, if I do 3 to the k power equals 81. So that means that 3 to the k power equals 3 to the 4th power. So k equals 4, which means this whole thing is going to be 4. So this gets replaced with 4. Then plus, this exponent comes out here, 4 times log base 3 of a, plus this exponent comes down here, so 1/3 log base 3 of b, minus, now this one here, I can actually simplify this also. So this is going to be 3 to the k power equals 27. So 3 to the k equals 3 cubed. So k equals 3, which means this whole thing comes down here as 3 minus 7 times log base 3 of c. So I still have to clean it up just a little bit more. This is going to become, the 4 and the minus the 3, that's really all I can combine here. So 4 minus 3 is 1 plus 4 log base 3 of a plus 1/3 log base 3 of b minus 7 log base 3 of c. There we go. And I know somebody asked this question the other day, does it matter what order they are written in? And the answer to that is no. Okay, I don't think I need to rewrite the other one. I think I can make that one fit. There was a lot of, that one got pretty long. So I'm just going to come back here. I think I can do this work here. One thing that you have to make sure that you do is distribute this exponent to every single little thing in here that you can. Some of you are not doing that, and that's throwing you off. So let's just go ahead and rewrite this. Well, I'm going to rewrite it. I know some of you don't need to, but that way I don't lose anybody. You got the natural log. This, everything's to the 4th power. So this e to the 4th becomes e to the 16th over x to the 4th times the square root of y to the 4th. Or the square root of y to the 4th power. It's the same thing. It doesn't really matter. And now if I'm going to take this and I'm going to expand it, I get the natural log of e to the 16th power, and then these are in the denominator, minus the natural log of x to the 4th, minus the natural log. Okay, so the square root of y to the 4th, or y to the 4th, I'm going to take the square root of it, that becomes y squared in either way, so this just is y squared. Then I simplify it a little bit more. The natural log of e, this right here, if I have the natural log of e to an exponent, I'm just left with what the exponent is, so this is just 16, minus the exponent comes down, 4 times the natural log of x, minus 2 times the natural log of y. And there is that. Then number 32. So we've got 2/3 log base 7 of m to the 6th minus 4 log base 7 of n plus 2 log base 7 of p. All right, so all these parentheses here are important and mean something, right? I'm writing it as a single logarithm, which means I'm condensing. This negative can be distributed, or you just know that this is minus all of this. All of this is in the denominator. I would suggest rewriting the exponents first, especially the more there is, just so that you don't get lost on something. It's going to give me log base 7 of m, and then this exponent comes up here. So it's already m to the 6th. So it's m to the 6th to the 2/3 power. So m to the 6th to the 2/3 power, even if you didn't write this part of it, make sure you think about what it means to be a power to power. This time we actually multiply them. Minus, and I'll leave my parentheses there, log base 7 of n, this would be log base 7 of n to the 4th, plus log base 7 of p squared. So now that I have this, I can make it all one single log base 7. So m to the 6th to the 2/3 power, I multiply those. So 6 times 2/3 is going to be 4. So this gives me m to the 4th in the numerator over n to the 4th p squared. And then that is condensed. Okay, so that completes your review. If you have any questions, let me know. I'm pretty confident that I didn't do anything wrong, but you never know. And I was interrupted multiple times. So, all right. If you can do this, you should be able to do well on your test tomorrow.